jump through them. How do we actually measure PSD, particle size distribution? You can do that by simple, old-fashioned sieving. Use a sieve to mechanically sieve it, okay, by the ability or inability for particles to pass through sieves with different opening size. These are probably you used it, or at least you saw them. Different sieves with different openings, okay, different mesh. And then quite often people can stack them up together onto a shaker, essentially a shaker. It would vibrate and shake, and the powders, you put it initially at the top and would gradually drop, right? Depending on the particle, the sieve fineness of the sieve, the most fineness would drop all the way to the bottom, and the most coarse would be on the top, just by gravity, okay? Very simple stuff, and you do see them for some industry productions in essentially the same principle. And the factors that impact include wire diameter, wire width, okay, opening width, which is between wires, how much opening that I leave open, and then the mesh number, how many wires or how many openings per linear length. Mostly people use English metric in inches. Okay, opening area, fraction area that is not blocked by area. And typically, your mesh looks something like this, woven together using wires. And A is my what? A is my opening width, and W is my wire diameter. Okay, and A in this direction, A is in the other direction. Of course, we can calculate the mesh number. Mesh number is 1 over A plus W. A plus W is your total repeating unit width, and for unit length, how many of them? That's a frequency, right? How frequent we can see that. On the other hand, the A, capital A for opening area is a percentage, is A square. That gives me my actual what? Opening divided by A plus W, that's my total area squared. That gives us a ratio. Okay, what's the percentage of the screen that is open? Okay, PSD by sieving, let's continue a little bit. It's used for sizing fine or coarse particles. Coarse, typically for coarse particles, very coarse. Not effective if the powders are smaller than 1 micron. I don't know whether you had experience using a sieve to sieve some fine particles. It quite often takes forever. Takes literally forever if you do it manually. Oh, even if you do it on a machine, it takes forever. You use a small plastic scrape and then go back and forth, back and forth, back and forth, and nothing goes down through the sieve. It takes forever due to what? Agglomeration. The particles come together, even though the particles may be finer than the screen, but they have a tendency to glue together by a simple van der Waals force, or cannot avoid it, clogging of your openings, right? If the particles just have a little bit of moisture, or not even moisture, just by van der Waals force, they have a tendency to glue the openings. And that's what makes the sieving sometimes very, very slow. Dry sieving, most of the cases, you can imagine with surface tension, it's going to clog even worse. Make sense? And time consuming. But you should still use the traditional ceramics for raw material specification. I visited some industry production. They do have larger scale sieving to sieve very coarse stuff. Not fine, very coarse stuff. Examples for selected sieves. Here, the table listed some of the mesh number, sieve opening size, wire diameter, and the percentage of openings. Quite often, you find the higher the mesh number, quite often, the lower the percentage openings. Okay, of course, it also depends on the wire diameter and other things. Other than sieving, people can get a PSD, particle size distribution, very important by some other techniques, such as very commonly light scattering. This is actually used a lot, light scattering. Light visible light pass through particles in liquid suspension, leading to scattering. So we all have probably experienced if we have a colloidal solution suspension and we shine a light, quite often you can see laser light. You can see the laser light in this direction. You can see the laser light in this direction. That means, okay, the light got scattered into other direction. And people use the fundamental principle can measure light scattering. We are not going into the detail. Okay, when the particle size is smaller than wavelengths, certain scattering, so-called Rayleigh scattering, Mie scattering, Fraunhofer scattering. We are not going to talk about detail. But anyway, incident light hit suspended particle, they're going to have scattered forward scattering, and they have different mathematics behind it if the particles versus the wavelengths satisfy certain relationship. I'm not going to into the detail, but that's a principle for some of the instruments that people use. Shine laser light and then going to split into certain directions, and people are going to measure them. Widely used for particles in this range from 5 nanometer, very, very fine, to thousands of micron. Okay, quite often nowadays automatic analysis. And other than light scattering, sometimes people use microscopy and do what? Image analysis, which means you have an ICM. You take an ICM image, essentially a photo of your particles, especially if they have comparable depths of view. If they are relative planar, you can do image analysis to get the particle size. Typically, optical microscopy for particles greater than 1 micron, because visible light, you cannot use visible light to image too fine particles. And then scanning electron microscope, anything bigger than 10 nanometer roughly, you can see with ICM. And anything further finer, you can use what? Transmission electron microscope. Okay? And image analysis need measurement on numerous particles. You take an image for many, many particles, not one, two, probably hundreds, even thousands. And right now, there are probably automated software using that comes with SCM that can do it. Okay. Different ways of defining sizes. Okay. And other particle size analysis method, sedimentation. If we have a suspension and the particles by gravity, they would have a tendency to drop in the suspension. And how fast they drop is related to the density as well as the particle size. But on the other hand, people can shine a light or X-ray onto the suspension. Shine X-ray onto the suspension, and the X-ray would be scattered in different way, and measurement of the change of the particle concentration with time to determine the particle size distribution. If all the particles are extremely fine, you may find my intensity doesn't really drop. Doesn't really actually increase because no particles settle. On the other hand, if all the particle quickly settles, my intensity would quickly increase. Initially low because it's blocked, but then quickly increase because it's clear. Everything dropped. By doing this time series, we can know it. Of course, these are specialized instruments. Nowadays, you don't have to worry about the principle. The vendors that supply this equipment, fully automated, computerized. Okay, you just know that's such a thing. And one day you may use something like this. Electrical sensing, Coulter counter, which is, okay, when particles like this passing through a narrow opening, there will be quite often a change in the local electrical resistance, and if you provide a constant voltage, there will be a sudden change as the particle goes through here in current, and people can use the similar method to measure particle size distribution for anything from 0.5 micron to 500 micron. People use it for actually blood cell counting. Okay. Okay.